one starting alkyne, two reagent paths, two different carbonyls. With mercury 2-catalyzed hydration, you get a methyl ketone. With hydroboration-oxidation, you get an aldehyde. Same skeleton, flipped regiochemistry. In this video, you'll learn the two main ways to hydrate alkynes, why both pass through enols, how tautomerization gives the carbonyl you isolate, and how to predict the product every time. Here is a big idea. Both hydration routes first make an enol. Enols don't stick around, they tautomerize to a more stable carbonyl. The only question is which carbon gets the OH initially. That's your regiochemistry. Now, let's discuss these two different routes. Route 1 acidic, mercury 2+ catalyzed hydration. Water adds Markovnikov, placing OH on the more substituted alkyne carbon. The enol forms rapidly tautomerizes to a ketone. Here's a quick example. Hydrating 1-propyne with mercuric sulfate in aqueous sulfuric acid gives Markovnikov addition, where water adds the OH to the internal carbon, forming the enol, propan-2-ol. That enol rapidly tautomerizes to its keto form, acetone, a methyl ketone. That's why hydration of terminal alkynes using mercury 2+, with mercuric sulfate in sulfuric acid, reliably yields methyl ketones. Here's a quick fix. Think of it this way. An enol is an alkene with an OH on a double-bonded carbon. That's why it's not stable as an isolated product, since C double-bond O bonds are stronger and more polar. The keto form is thermodynamically favored. So far, we've covered how mercury 2+ in acid drives Markovnikov addition, how the enol quickly tautomerizes to a ketone, and how terminal alkynes end up as methyl ketones. Want to turn those milestones into mastery? Tap the link to access the practice test, flashcards, and study guide, then jump right back into the video. Lock in what you learned and keep going. Let's continue to route 2 hydroboration-oxidation. It begins when a bulky borane adds across the triple bond. After oxidation, the OH group is placed in the anti-Markovnikov position on the less substituted carbon. From there, the enol tautomerizes into its keto form. For example, in hydroboration-oxidation, react 1-propyne with 9-bora-bicyclo-3,3,1-nonane, or 9-BBN. The boron adds to the terminal carbon in anti-Markovnikov fashion in sync with hydrogen. Next, oxidation with hydrogen peroxide and sodium hydroxide replaces boron with OH, forming a terminal enol. That enol then tautomerizes to propanol, an aldehyde. This is why terminal alkynes under 9-BBN with hydrogen peroxide and sodium hydroxide conditions reliably furnish aldehydes. For internal alkynes, there's usually no strong regio bias. A symmetrical internal alkyne, like 2-butyne, gives a single ketone either way. Unsymmetrical ones can give mixtures because neither carbon is clearly favored. Here are some things to watch out for. Use a bulky borane, such as 9-BBN or dicyamylborane, to stop at the vinyl borane and avoid a second addition. Under acidic conditions with mercuric sulfate, remember the reaction follows Markovnikov's rule. And finally, keep in mind that the enol is only an intermediate. Quick recap. Choose the pathway that places the OH exactly where you want it. Remember, the enol will always convert to the keto form. And don't forget to check. If the alkyne is terminal, you have control. If it's internal, expect a mix. That's hydration mastery. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.